We're going to continue our conversation about minors and contractions. Now, today's video, the title is kind of a pun, but don't let it mislead you. When I say that we're going to cover some minor facts about minors, don't take that to mean that these are somehow uninteresting, boring, or unimportant. In fact, they're going to be very useful for us, but they're not immediately obvious how we're going to use them to get to our big goal of this part of the course, which is to prove Kuratowski's theorem and Wagner's theorem about minors and topological minors that characterize planar graphs. So the two main facts we're going to learn are that degree 3 minors, that is, if I have a minor of a graph that's a degree 3 graph, that's actually a topological minor. That I can realize that as a minor using only topological contractions. Those are the contractions that contract paths. Now, the second one is that if G is 3 connected, then there is some edge in the graph, such that if I contract that edge, I get, in the end, a 3 connected graph. All right, so these are our two big facts for today, but in order to get into them, first, we're going to learn a new concept, something I call a minimal preimage of a contraction. So F here from G to H is going to be a contraction, right? A surjective simplicial map such that the preimage of a connected graph is connected. In particular, of course, that means that the preimage of every vertex is some connected graph. So here's an example down at the bottom. I've got G as this graph here, and I've circled the preimage of each vertex just to show how the map is working. Okay, so this little K3 here maps to this vertex, this little graph here. I guess that's K4 minus an edge, maps here. The single vertex on the bottom maps to the single vertex on the bottom. All right, so that's an example of a contraction. Now, the minimal preimage of this contraction is going to be the subgraph of G, the smallest subgraph. It's not actually globally small, so it just means I can't take anything else away from G. So I'm just going to remove vertices and edges from G, so long as I still get the same map serving as a contraction. Another way to think of this is to remember that to be a minor, you actually have two steps. You can first take a subgraph and then apply a contraction. And so here we have a contraction, but instead we're going to use this power to first take a subgraph, and we're going to try to get that graph as small as possible. So one subgraph, I've highlighted it lightly in yellow, but you can't see it probably in the video. So let me redraw what it was. I took just this bit of the graph right here. So it looks like this. 1, 1, 2, 3. Again, this is not minimum, but it is minimal. So if I took this subgraph of G, this is some G prime sitting inside G, and I could take the same map to contract this to H. All right, so this is how we find a subgraph that's really as small as possible. And you could do this if you want to actually construct one. You could do it in a greedy way where you just look at every vertex and ask, if I remove that vertex, is the map I have restricted to the subgraph I'm left with? Is that still a contraction? And you'll notice a couple things, like some vertices got tossed entirely. I had a couple vertices, like this one was gone, this one was gone. Notice this edge is gone, this edge, this vertex, this edge. So a lot of the graph just got eliminated. Okay. So why is this useful? Well, there's a couple of things we know about the minimal preimage of a contraction. It turns out that there's certain structure that must be present. In particular, if you look at any vertex, so here's a vertex, it had some subgraph, some connected subgraph that was contracted to a single vertex, but the preimage, in the minimal preimage, the preimage is going to be a tree. And I think this makes sense if you recall the definition of a contraction was that the preimages of connected graphs are connected. So if it has to be connected, but it's also minimal, well, the minimal connected graphs are trees. So in this case, I could eliminate this edge, and it would still be a contraction from this graph to the vertex. Now it may be that more of this tree gets eliminated as well, but it depends on what's adjacent to it. The other thing we know is that if you look at a particular edge, let's look at this edge here, in a contraction, it could be that the preimage included multiple edges. That is, here I have two edges that both get mapped to one edge. But in the minimal preimage, the preimage of an edge is a single edge all by itself. So I could just remove one of these edges, as I remove this one, and the mapping is still a contraction. All right, so this is going to be very useful for us because now when we talk about any contraction, and if we're only concerned with questions about whether or not it's a minor, or in fact also we can also do this for topological minors, but if we only care about whether or not it's a minor, we know that we can first remove anything that's not in the minimal preimage, and that way we can know a little bit more, or at least assume a little bit more about what structures must be present in the domain of the contraction. All right, so that brings us to our first lemma, the first of our minor facts about minors, and that is the following. If G is a graph with maximum degree 3, if G is a minor of some other graph H, then G is a topological minor of H. In other words, degree 3 minors are topological. I think that's how I wrote it on the intro slide. We already know that if you reverse these two symbols, that's an obvious statement. If it was a topological minor, then clearly it's a minor, because minors are more general. But in this case, it's saying that if you have a degree 3 minor, then there's some subgraph that contracts to G, some subgraph of H that contracts to G, that only has to contract paths. So I've drawn an example here to get us warmed up. You see, here is a graph. This would be G. It has maximum degree 3, it has just this one vertex of degree 3. And say here is our contraction. Now, just having a contraction, that's enough to say that G is a minor of H. But if we were to look at the minimal preimage, we could pick out, well, these vertices all stay the same on the outside, but we could pick out some subgraph. For instance, maybe this might be an example of a minimal preimage. It's not a unique minimal preimage, but it is minimal. I can't remove any other vertices or edges and still have the corresponding map be a contraction. So this is a subgraph of H. It's our minimal preimage. And now you can at least see in this particular case that the contraction from this graph to G is a topological contraction, because now all I have to do is contract this path to a single edge like this, and I contract this path here to the single edge here. So on the minimal preimage, the contraction is topological. So that will be the general form of how you would go about proving this. I'm not going to do it in detail here, but you consider the minimal preimage of the contraction. And there's always is some contraction when you're talking about there being a minor. Take the minimal preimage of that contraction. And if you like, you can also think of this as having one more step where this is really H prime, which was a subgraph of some bigger H. But when I look at that minimal preimage, then what happens is, since the degree 3 bound on G exists, then every tree, just remember that every tree with 3 leaves is a subdivision of the star S3. And so when I look at the minimal preimage of every vertex, and I look at that vertex's preimage plus the single edges coming out, I'll get S3 if the degree is 3. If the degree is 2, that's fine too. The contraction still be topological. All right, so this is an important fact for us, and it does imply something immediately that I think we haven't proven yet. Well, there's first the immediate corollary, which is that K33, if K33 is a minor of your graph G, then it's also a topological minor. We knew the other direction, okay? Like I said, this way we knew. But since K33, the complete bipartite graph with 3 vertices on one side and 3 on the other, because that graph has maximum degree 3, in fact has degree 3 at every vertex, then if you have that minor, then you have that as a topological minor. And so now that implies, for example, if you have a K33 minor of any kind, doesn't have to be just topological, then G is not planar. Because we've seen that if you have a topological minor of K33, because K33 is not planar, then you know you're not planar. Now it suffices just to be any old minor. So I can, any way I contract the vertices to get down to K33, then I could have removed stuff first and then found that as a topological minor. So this is, in a way, it feels like it gets us halfway to something like Wagner's theorem. Now let's do a quick sanity check, just to be clear that this is maybe not going to be everything we need for proving Kuratowski and Wagner. You see, because it's not true for K5. And we saw this actually already. So if I have a graph like the Peterson graph, this is a graph that we've seen. It has max degree, well, it's 4. Actually, it's constant degree 4, right? It's 4, not 3, right? So I can't hope to get this same kind of result for other kinds of minors because we know that this has a K5 minor, but it does not have a K5 topological minor. Right, in that case, we had to content ourselves with just a K33 topological minor.